Hello everyone, my name is Anthony Shivkumar, and in today's video I thought I would do a video on the introduction to say using a SPICE software such as ADS. And since I've been dwelling a lot more into signal integrity, I thought it would be a good idea to show how using simulations can help you better design your PCBs. Because one of the things that I had been doing was I was just designing my PCB, say through any CAD software, sending it to the fabricator, and sometimes it would work and sometimes it wouldn't work. And I would get my ideas of how to design these PCBs based on reading app notes, based on some high-level principles that, do this, don't do this, don't do this, kind of following some form of guidelines without really understanding why those guidelines are in there in the first place. And then more I read these app notes, I find that many of them are contradicting, and I didn't have enough intuition to really know, when should I apply which guideline, when and where. And this made me dwell more into the path of, okay, I need to understand this right from the concepts, right from the physics, right to so that I can write my own guidelines based on the systems that I'm designing and based on the electronics that I want to make and based on the requirements that these electronics will be subjected to. So having said that, one of the key features of being a good electronic designer is, first and foremost, there's no substitute for actually making these things. I think that's still a very important criteria if you really want to be really good at it. But another thing is, before you fabricate the board, it's not a bad idea to simulate some of the concepts or simulate the performance of your board. Using a 2D field solver or a 3D field solver, understanding, what are the possible issues that could arise, be it, signal integrity, be it power integrity, be it EMI, or whatever you're exactly trying to test. So having said that, this video will be an introduction to one of those softwares, which is the Keysight ADS. And you can do a lot with it. You can take your, if you design a PCB, you can export those files into ADS, and then ADS can create some models for you, and then you bring them into the SPICE part of the software, and then you can do some more detailed analysis. So before we even get to more of those complicated analysis of bringing in your own CAD drawing into the system, into the software, and doing all this analysis, I thought it would be a good idea to just show an introduction of the workspace of ADS and how everything works in that. So you get a idea, or get your hands dirty in using the software right from the introduction level, and then from there we'll build up on doing a lot more complex analysis. So as soon as you open the ADS, it'll tell you what you want to, where do you want to create your workings directory, and what's the name of your cell in this particular case. So I'm just going to put this RLC circuit, and I'm going to create a workspace. And then you'll be greeted with just this, basically this particular window. And from here, what we'll do is we can create a new cell, a new schematic. And a schematic is based on certain cells. And in this particular case, I'm just going to put here, say, RLC. It's very similar to what I did in the previous video. But in this video, I'm just going to go step by step as to how I made those circuits in the previous video. Once you click on schematic, you'll be greeted with this particular window. And here is where you have your workspace of creating your own, all your schematics you want. On the left-hand side is where you have the different types of components that you want to place. And then on top, you have things of where you can, add in, say, a ground, a variable, and do some simulations as well. So we're just going to do something very simple. What we want to do is some basic transient analysis, very similar to what I did in the previous video. So the first thing you want to do is go out there and say, what kind of simulation are we going to perform? So in this particular case, I'm going to click the simulation transient, and I'm going to drag this in here. Now what this tells ADS is, and if you want to escape, just press the escape button, and then that particular cursor will be that particular function will now be aborted. Otherwise, it'll keep copying the same component again and again. So just press escape. There are other ways to do it, and as I progress through the software, I'll show you different ways of exiting certain functions. So here what we have is a transient response, and this is important because the way ADS or any SPICE simulation works will be based on what you're trying to simulate. And if you're trying to simulate a transient response, say in the picoseconds or a nanosecond, then you really want to just simulate based on picosecond and nanosecond. And say, for example, your step response is going to be something that's going to happen, say, in 1 nanosecond, and you want your stop time to be after 1 second, then that's a lot of simulation samples, and it'll take a long time. So you need to be aware of your of your sampling time and the total time you're simulating for, as based on what you're trying to simulate, it can take a long time. So right now here I've got this as 1 nanosecond. So every nanosecond is going to basically do the simulation. And once it reaches 100 nanoseconds, it would stop. So you're basically having 100 samples, if that makes sense. So now we're going to do a basic simple RLC circuit. So I'm going to basically create a source. And then here in the source, let's create a step response. Now there are different things you can use. You can use pulse, you can use voltage DC, but in this case, I want to do a step response. And in here, there won't be any delay. That means it'll rise exactly at 1 second. When you double click on this, it'll give you different options as to how you want your rise to be. You could have this as nanoseconds. You could have this as so you're basically putting this as 1 nanosecond. When do you want it to step response? What's your voltage high? And what's your VLOW? Now, what this might do is it might give me a very smooth, almost instantaneous rise time. And maybe that's not what we want, because that's not how real circuits work. A real step response will have there will be a rise, a rise, it won't be instantaneous. It would happen, over, say, a nanosecond or a picosecond, but it will not be continuous. There'll be a time before it goes from 0 to 1. And this particular function called the pulse allows us to characterize how you want your pulse to be. So in this case, we don't want it to be linear. We want it to be, say, some form of, want it to take a gradual curve from going from 0 to 1. And what we're doing over here is using an ERF function, which is basically kind of like a, we can also click on help, and the help will tell you what that function does actually. So it's opened up in the different video, and here it'll tell you what each function does. And here you can see that the ERF function has got a little bit more of a, a little bit of a curved it's got a more of a natural way of how a step response might happen in real life, somewhat simulating that. So that's the kind of function that we want to do. Is instead of a rise time and a fall portion being linear amps, this source generates a pulse based on the error function, giving a different shape to the rising and falling edge. By not having abrupt changes in the slope, the pulse shape is more realistic and its frequency spectrum decreases more rapidly. So that's what we're really trying to simulate, something a little bit more realistic in that sense. So we can close this window up. So we want the V high to be 1 volt, which is fine. The rise time is going to be 1 nanosecond and the fall time is going to be 1 nanosecond. This is where it's important. We want the width to be, so we don't want it to be pulsing within this transient response. So what I'm going to do is basically create a width of say 100 nanoseconds. So the width of the whole simulation. And the period could be, say, 200 nanoseconds in this particular case, 1,000 nanoseconds. It doesn't matter as long as it's a little beyond, say, my transient response. And then for the rise time, I'm going to make this as a variable, and I'm going to put this as RT underscore nanosecond. So it's basically RT stands for rise time and nanosecond. So I will talk a little more about how do we create variables, because once we create variables, we have the ability to use something called a tune, and I will explain that also in this video. And then we're going to click OK. All right. In this particular case, I'm going to put a simple resistor. So we're going to go through the lump circuit components, or the lump components. And here we have, say, a resistor. And if I don't do anything, you'll see the same component repeating again and again. So I can right click and then I can click End command. And then from here, I can put a simple capacitor. So we have a RC circuit, and same thing. I can do this and click End control. And if I want to rotate it, I just right click and then I click rotate. And then from here, if I want to draw the wires, I can click on this wire button over here. And this will basically connect the wires. And then we have, say, one from here to here. All right. And now what we want to End command. And then we want to add the return path. So the return would be, we could have one return over here, and then the other return over here. And similarly, we could end the command. Okay. Now we want to label the model. So what I'm going to do over here is just click a name. Okay, so what it says is, so I'm just going to put over here, and I'm going to put here as V in A, because this is the A circuit. And I'm going to put here V out A. Okay, so we have a simple RC circuit, and I'm going to basically put a variable over here. So I'm going to make this as resistor underscore A. So this is a variable, and the same thing, I'm going to make this a variable too. So I'm going to put this as a capacitor underscore, say, picofarads underscore A. So now that we have the circuit set up, now it's time to fill in these values, such as the rise time in nanoseconds, the resistance, and the capacitance value. And to do that, we click on this variable option over here. And I'm just going to place this anywhere. And in here, I can double click and we can add our variables. So I could just basically click on, say, rise time. No, it's RT underscore nano underscore seconds, which is going to be, rise time can be 1 nanosecond. And then we have R underscore A, which is going to be equals to, say, 10 ohms. And then we have your C underscore power in picofarad underscore A, which is going to be, say, 10 picofarad. I'm just going to click apply, and then I'm just going to click OK. So these are how all my variables are now set. And so we've got the RT underscore, wait a minute, nanoseconds, R underscore A ohms, and then this is going to be in picofarad. And let's do a simulation. So you press this gear button to simulate. It'll open this simulation window. And once the simulation is done, it'll open this particular page. And this is now the workspace in where you can plot graphs and plot your analysis based on what you want to plot. So here we'll just click the table. And as soon as you click the table, it'll tell you what do you want to plot. So I want to plot my V in, that is my step response, and then we'll plot my V out, which is the analysis or the voltage across the capacitor. And then when we click A, it'll give you this very linear curve, which is not what we were expecting, but we'll analyze and see what is really going on. So here we have both is going to be in, it's a nanovolt. We have here as 0 to 10, So let's look at what's happening in here. So ideally we want a step response which should go from 0 to 1 nanoseconds. Our rise time is in nanoseconds. So let's have a look whether it is in nanoseconds. So whenever you have these types of mistakes, because we can't really always trust the simulation, is very important. So here's number one issue. So I've not basically said that this has to be in nanoseconds. So it just put in 1 and not too sure what the 1 was. So the unit is important. So because the graph did not make sense to me, I need to double check, whether the graph is making sense. So now that 1 nanosecond is a nice step response. And then let's do the simulation again and see whether we see an improvement in what we're doing. However perfect you are, and now it looks a lot more like what I would expect. Now, since this graph it's auto scaling over here, which is not the best, what do you say? Table or so what I'm going to do is just adjust some of the things a little so that it's more readable to me, in the sense that I'm going to if you just click on this, you have you can make some changes. So I'm going to make this as -1, 0.1. So there is some space before it starts, which is now looking a lot better. And since we're simulating every 1 nanosecond, the sampling is going to be every 1 nanosecond. So if you want to have a little bit more smoother, because as we zoom in, you can see that it's so the blue is the V, and so the blue is the V out and the red is the V in. So let's increase our sampling time a little bit. So what I'm going to do is just minimize this window, and I'm just going to increase the sampling, the maximum step type, or rather decrease the sampling time, and let's make this every make this maybe every 0.1 nanosecond. This is going to take a little while, and let's see what happens. And instead of doing this as 10, because we're going all the way down there, let's do it till 50. So instead of 10 nanoseconds, let's make this say 50. And so we basically reduce the thing by half. Yeah, so now we're basically looking at this curve. So let's maybe make this at 20 and see, because we're reaching the steady state pretty quickly. So we can simulate a little bit more just for a shorter period of time. And now let's simulate. Yeah, and now it's looking a lot more better. So from 0 to 20 nanoseconds, we're looking at this step responses almost to 1 over here. And yeah, and as you zoom in, you can see that this is how, as a step response is, we have a 0.0 to 1 in 1 nanosecond. The response of the red, the blue is the response, and there's a slight delay. So now say, for example, you want to play around with this values of R and C, and you want to adjust it accordingly based on real time. You want to tune it based on some parameters. So you can click the tune function over here. And the tune parameter is something that, so what I'm going to do is we're going to tune the rise time. We're going to tune the resistor, and we're going to tune the capacitor. So this is one way where you can, and then you can just click escape to, so now we're in the tune mode. And now this is a very nice way to look at how your circuit is responding based on tuning parameters. So where do we have this? So what I'm going to do is bring this over here so we can see this. Bring this over here and actually bring this right on top. So now we can all see what the tune is. And one thing that we'll notice is we can play around with the maximum value and the lower value. But let's play around with, say, the resistance. And as I increase the resistance, you can see that it is taking the smaller the resistance, the more closer it is to the step response. So as I increase the resistance, then there's some form of a delay. So you can almost think of, as you increase the resistance, it'll take some delay before it reaches the step. Now, what happens about the capacitance? The capacitance will also, if I increase the capacitance, what do you expect to see? And again, once we increase the capacitance, you can see that it takes a little longer time to reach the step response. So that's why we have something called as the RC time constant, because if your RC, R into C is small, then it will respond to the system faster. And if the RC is big, then it will take a little longer time to respond to the system. And as we can see, as we keep increasing the, so let's take the maximum value as, say, 150. And just say 150 picofarad. And now when we increase this completely, you'll see that it's taking a lot longer time. So, and that's the RC time constant. So if you want the system to respond much faster, you just have to make sure that your values of your resistors is smaller. So this is how you can do analysis just by using your intuition based on, the literature that you read, and then doing your simulations to really understand how this works. And the whole idea is to predict before you actually do this. You don't want to build your intuition from the simulation, rather use your intuition and then conduct the simulation. And that's a much more appropriate way of doing this stuff. Let's do an RLC circuit in this point in time now. So this is the way that you can simulate, and you can see how powerful the system is already, and how you can, make your intuition a little bit more stronger by saying, okay, this is the circuit that I'm building. These are my parameters. There's no substitute for doing some of these hand calculations, especially if it's a simple RC circuit, something that I've done in the previous video. And then over time, try to build up your intuition by first predicting what you expect, and then look at the analysis to see whether it resonates or it works or it aligns with your thinking. Just as in the beginning of this video, we did not put nanosecond and the graph was not making any sense. If you don't have that intuition, you won't know whether the graph is making sense or not. So by having some form of intuition, you can at least have an idea, okay, this graph is making sense, because as you do more complex circuits, how are you going to test certain parameters, whether it's making sense or not? How do you know whether your parameters are right? Because you could just have a parameter wrong and will give you a wrong graph. And without that intuition, you won't know whether it's giving you the right information or not. So it's a good idea to do some consistency check and test to make sure that at least the things that you understand, you can make sense of out of it. So we'll do one more analysis. We'll do a simple RLC network right now. So what I'll do is I'll just drag this to the right. I'll put this to over here. And I'll remove this. I'll put the L model. So we'll put an L over here, and we'll see how this works. So we'll put an L over here, and then we'll connect it through the wires. Take the wire in here. Connect wire 1 to wire 2, and wire 1 to wire 2. And we can put a variable over here. I'm going to put one right over here, and this is also going to be V out A. If we want to see what the voltage is across the inductor or the current through the inductor, we can put, say, VL underscore A. And from here we can now simulate. So it's 1 nanohenry, okay. So what I'll do over here is, so we'll try to tune the RLC circuit as well. So we can double click on this and we'll make this a variable too. So what I'm going to do is put here as L underscore nanohenry. And this is important because we want this to be nanohenry. So now it makes sense when we change the variable. we know it'll be in nanohenry. So in the VAR equation, I am just going to go to name value or standard. Name value, and in here what I'm going to do is click here as L underscore nanohenry is equals to say 1, and then we click apply, and then I click OK, and here we have here nanohenry equals 1, and for the tuning parameter, so we'll just simulate first, and then before we do some tuning, and just see what do we expect. Yeah, so now you can see that there is some form of overshoot and then there's an undershoot before it settles down. And one of the things that we need to understand over here is that this can be a resonant circuit because it's an LC circuit. And let's try to play around with the parameters to, just try to see how the circuit changes based on if we change the parameters. So I'm going to make sure that we use the tuning function. And I want to add the inductor to the tune as well. So I'm just going to click on the inductor, and then we'll have all the 4 tuning parameters. And then I'm going to open the window where the simulation is. Yeah, perfect. And now let's do some simulations. So we have R, we have A. Let's see what happens when we increase the inductor. So as we increase the inductance value, we can see the overshoot is increasing, or the ripple is increasing. And if we decrease the inductor, we're getting more and more into a pure RC circuit. So you can almost think of the inductance adding some form of resonance as we increase it. But what happens if I increase the capacitance now? So as we increase the capacitance, you can see that the time delay of the circuit, or the circuit response, becomes a lot more smoother, or it takes a little longer time, but the overshoot is a lot less. So this is how you can play around with this. Now, clearly, I am trying to make my judgment based on the simulation parameter itself, but you need to do it the other way around. Now, what does the rise time got to do with all of this? Now, what if I decrease the rise time? Will the overshoot decrease or will it increase? So let me try to decrease the rise time. And now you can see that the overshoot is actually increasing. So this overshoot is not drastically increasing, but it's increasing as I'm bringing the rise time a lot smaller. So what if I make the minimum, say 0.1 over here, and then keep decreasing this? So as I make the rise time smaller, you can see this overshoot is increasing a little bit. And if I increase the inductor is a lot more. Now let's make it a little bigger, and now let me increase the rise time. So now I'm increasing rise time. Let's bring the rise time a little bit. And then you can see that the overshoot is decreasing. So that means there is a correlation between the rise time, the peak of the oscillation, and the swing. And this is important when we're looking at ringing and doing some TDR analysis reflections. You'll realize that this overshoot and this undershoot is very dependent on the rise time. So when we're doing signal integrity and analyzing our circuit, it's very important to understand the rise time, because the rise time can cause a lot of these ringing, and a lot of the parameters based on signal integrity is based on rise time. So if you're just doing traditional RLC circuit, you really wouldn't care too much about the rise time, because we could have a slower rise time for most circuits. When it comes to signal integrity, we're looking at high-speed signals. These things can switch at a very high speed, so the rise time becomes a very important parameter that we want to focus on, and then design our circuit so that we can minimize this ringing effect. And that's really what I wanted to show you as to why an RLC network or system is so important, because this can definitely help us understand our intuition of how these types of graphs or these types of behavior happens in the system, and these can be modeled very simply through an RLC system and RLC network. And that's the importance of understanding this type of circuitry. In the next videos, I'll try to basically talk a little bit more about bandwidth and what is a step response of a bandwidth. What is the bandwidth of a step response? Because the step response in the time domain is very straightforward. I mean, this is I'm using the time over here. Don't ask me why I've been. So I'm just going to center this, zoom this a little bit. Yeah, this is how I should have been doing it actually. I'll be talking about the bandwidth. What is, if in the time domain, it just looks like a step response, but in the frequency domain, when we do a frequency sweep, what all frequency components basically makes this particular step response? And in simple English, if you do a Fourier transform, it's basically saying how many different types of sine waves and the amplitude makes up this particular step response. And then we'll go a little bit more into detail as to understanding what bandwidth is with respect to a square wave or a step response, because once we analyze things in the frequency domain, it'll give us a lot more information. I hope this introductory video, helped us get you understanding how ADS works and how a SPICE simulation of any of software like this can really help you understand your intuition, make you understand some of the concepts in a much more intuitive way. And you can play around with this without fabricating every board to really test this out. I'm not saying that you shouldn't be doing that. I think everyone should be actually making these things rather than just being a button pusher and pressing buttons. And I think both you need to make as much as you need to, do the simulation. But it's good to do both and not just be one or the other, to really make sure that when you're designing something, you're doing your analysis, and at least you're confident in your analysis. So if something is wrong, there's a gap in your knowledge and you know exactly where you want to fix certain things. And if you don't have that intuition, then you'll just be making boards blindly and hoping it will work. And that may not be the best way to go about doing this thing. All right. And that's all there is for me today. Stay tuned, because there'll be a lot more videos of this sort, primarily because I'm delving a lot more into this type of analysis. I hope you like this video. Please subscribe if you like and you want to know more about how I'm progressing. Hit that subscribe button so that you'll be notified every time I release a new video. And stay tuned and keep safe. Thank you.